you got a quiz yet?
No, he doesn't give us quizzes.
Are you serious?
Yeah, it's just all tests.
Yeah, mine is 6% quiz, everything else is exam. And the final, apparently there's one professor at the final is optional. My final is 30% of the whole grade.
Oh, okay.
So
That's the thing with differential equations is that, and this is something you guys don't know because you guys were probably in middle school, but in 2007, that in 2007 it was only around that time when Calc 2 started to coalesce as a giant lecture class, and Calc 3 was still a bunch of different professors teaching Calc 3. Then Calc 3 happened, that was about 2011 when that coalesced into one class, and Williamson was actually in charge of that class. But it was very, very difficult. In fact, a lot of people complained about Williamson that they switched this professor out with Kieran. Kieran started taking over that, so you guys already know that because you probably had Kieran recently. But they haven't done that for DiffyQ yet. That it's just 12 different sections, and depending on who your professor is. So with that in mind, I'm going to try and hold these every week or every 2 weeks, just so I can keep you. Many of professors are going at different paces. But usually the first week of differential equations resorts to talking about vocabulary, and that's what this first page is all about. I'm going to go, I don't know why, I think the staple's in the wrong place. At least it is on this. Okay, fucking who cares. Did you guys have like a discussion about vocabulary? Was it expected that you're going to need to know what that's going to, okay. So let me go to the vocabulary briefly. We'll start with derivative. We all know what that is? Okay, we'll skip that one. Derivative just means a measurement of rate of change, and rate of change is synonymous with that term. And especially when you see the term rate of change in a problem, make sure that means derivative to you. In this class, we're going to be dealing with a lot of, let's talk about dependent variables. A dependent variable, usually y, and the independent variables you're dealing with, usually are x and t. So you're often going to see dy dx. But eventually you're going to switch into dy dt. This is kind of weird because, and it's almost really strange. You guys have the book yet?
I
use it
online.
Yeah, good, because there's a link that I've actually got in my Google Drive that I forgot to put that on there. The textbook is available online, but some people like to have a physical copy and lug it around. Anyway, dy dx, you do this a lot. You've probably seen it since Calc 1, and then somewhere in chapter 3 or 4 they start using this, and you don't think, no one explains why. You're just, oh, you know what? They switched from x to t. Is everyone going to talk about this? No? No? We're going to use t now? But that's what happens. So independent variable is your denominator, and the dependent variable is the numerator. And almost all your differential equations are going to be done with y. Family of solutions. So this one, remember when you integrated 2x, you said, oh, that's x squared, but you said x squared plus c. This is a family of solutions. So x squared is what shape? We're going to do this all over again. Parabola. Here, but at least it's not 3D anymore, right? Parabola. But it's a whole different set of parabolas, all that are just shifted up or possibly shifted down, depending on the constant c. This is a family of different parabolas to form x squared plus c. Depending on the value of c, you get a particular member. So this is a family of solutions, but if I gave you some sort of initial condition, namely, maybe I told you y of 3 equals 14, then that would tell you that c equals 5. Because you just plug in 3 for x, 3 squared is 9, 9 plus c is 14, solve for c gives you c equals 5. So that tells you y equals x squared plus 5 is what's called a particular solution. Have you heard the term particular solution before? No? Well, now you're learning. This is general solution, particular solution. You can write that down. This is a general solution. And when they want a general solution, they don't care that you find the constants. When they want a particular solution, which this is, when they want you to find a particular solution, okay, my camera's doing fine. I might have to stack it up on some books later, but whatever. When they want you to find a particular solution, you're finding the values of the constants based on what are called some initial conditions. Cool? Ordinary differential equations, I don't know why I wrote a whole huge paragraph for this one, but ordinary differential equations just don't have any partial derivatives in them, which is nice because, well, I guess you guys are pretty good at partial derivatives, but you're not going to be dealing with any differential equations that contain partial derivatives. So if you saw something like, this is y double prime plus 3y prime minus 4y equals t squared. That's considered an ordinary differential equation. It's also, we'll actually classify this a little bit more, we'll leave this up here. Whereas if I gave you d squared y dt squared plus 3 dy dt, partial y partial t plus, or rather minus 4y equals t squared. This would be considered a partial differential equation since there are partial derivatives in it, right? You're not going to do any of these in this class. We're going to do any of those, which is nice. They actually have their own course here you have called partial differential equations, or it might just be called intermediate differential equations, but that's for a different, you don't do any of those. This as an ordinary differential equation, we can furthermore classify it by its order and whether or not it's linear. What is the order of this differential equation? Order 2, because we see the highest derivative being taken here is 2. So this is a second order. It's second order. Moreover, notice that if I put an extra derivative here, that would be third order. If I put 4 derivatives, that would be fourth order. Sometimes if I said fifth order, you don't want to put 5 tick marks, you might see this notation. That just means not y to the fifth power, but 5 derivatives of y. Make sense? This is distinguished from this, which is y to the fifth power. So if you see parentheses around the 5, that means they're looking at the fifth derivative. Anyway, let's go back to this double prime. Furthermore, this is a linear differential equation. This linearity is a harder thing to detect for a certain differential equation. Here's why. We're going to examine each derivative. Okay, try this again. We're going to examine y and all its derivatives. What's the power on this y? 1. And how about y prime? What's the power on it?
1.
Now the power on this y double prime. All 1. The powers on each y and each of its derivatives are all 1. That's good. Otherwise, it would be nonlinear, but this is linear. Let's take a look at some examples that are nonlinear. So we'll take a look at y triple prime cubed plus y times 3 minus y prime plus cosine of y double prime. Now let's do 1 over y plus equals t. Okay. So there's a lot of reasons why this is a nonlinear differential equation. First off, we all see it as third order, right? Three derivatives. It's nonlinear because we see a 1 over y. What's the power on this y, really? Negative 1. So this is nonlinear because of this guy, right? How about the power on this y triple prime? It's a 3. So that's also a nonlinear case. Does this seem to be an issue? I didn't mention this earlier, but if I distribute this y to the inside, I get 3y minus y times y prime. That's okay, but this is what I call an interaction term, and you're not allowed to have these either. You're not allowed to have y in any of its derivatives multiplied by a y or in any of its derivatives. So I can't have a y prime times y double prime. I can't have a y triple prime times a y. No y's can be multiplied together. So this would be what I call an interaction term. Can't have those. That makes it nonlinear as well. And lastly, this is cosine. You might say, okay, well that's y double prime to the first power, but it's stuck on the inside of some function that isn't to the first power. I'm taking the cosine of that. And if you think back to power series, let's not worry about power series. We'll talk about that later. You're not allowed to have y or y double prime or y anything inside on the inside of some trig function or some exponential function. You can't have e to the y, you can't have ln of y, you can't have cosine of y or sine of y or square root of y. So there's a lot of reasons why this is a nonlinear differential equation. Okay, I think we're done talking about that. We're going to talk about identifying first order. Okay, so this is just pretty easy. Let's just look through this one. Which of the one is a linear first order differential equation? Why is it not A? What's wrong with A? Remember, we're looking for a linear first order.
Because it's being multiplied to x cubed.
No, x cubed is actually fine. You're allowed to have that, and I probably should have mentioned this earlier. T squared y double prime. Yeah, I see what you're saying.
As long as it's not y.
Right, as long as it's not y. So she was saying t squared looks like a problem, right? But t squared is fine. You're allowed to have a squared on the t. That's your independent variable. So long as you don't have any power other than 1 on your y double prime, that's why it would be fine. It's not so much a matter of the linearity decision.
Oh, yeah.
It says first order, right? Yeah. First order. Let's start there. It says first order, but this says y triple prime, so it's certainly not A. Because A has a third derivative, so that's certainly not first order. B, y prime plus sine x times y equals e to the xy. Is it first order?
Yeah.
Yes. Is it linear?
No.
The first two terms are linear, but the e to the xy on the other side is e to the xy, non-linear. Again, this y here is to the power of 1, but it's trapped on the inside of some exponential e to the xy. And again, if you want to think about it in terms of the power series of e to the x, it's been a while, but e to the x is 1 plus x squared over 2 factorial. You guys remember this? Oops. Barely remember this?
Yeah.
And so on. So what would this mean? This would mean every instance of x is replaced by xy. What would you have then? You'd have an xy here, which is okay, but then you'd have an xy squared, that's not allowed, an xy cubed, that's not allowed. So you can have any y cubes, and you can think of it in terms of the power series. Basically, you need to have y or y prime, y triple prime, all those derivatives all by themselves, not on the inside of any other function. All right, so B is nonlinear. How about C?
Is that fine?
It looks good to me, yeah. Y prime, that's a first order. Nothing's being done to y that is being raised to some power other than 1. It's not trapped on the inside of any of the functions, so we're all good there. And then certainly d is wrong because we have a y prime raised to the second power. So the answer is C. Good? All right, now how do we solve these first-order linear differential equations? Before we go to work on solving these types of differential equations, we always want to be given a particular form. Namely, we want to work with the form dy dx plus some function of x times y equals some function of x. So here begins the method. Step 1 is to divide through by whatever method is chilling out in front of the dy dx. This will give us the correct form. So let's start with problem 2 using that step 1. We see that the differential equation given is, it's right over here on the board, let's say 4x dy dx plus 2xy equals
5x squared.
5x squared. And given we were given an initial condition of y of 0 equals 2. Okay. Step 1 tells us we divide through by whatever is chilling out in front of that dy dx term. So we're going to divide through by 4x. This is going to give us dy dx plus y over 2 equals 5/4 x. We all agree to that? Step 2 says, multiply both sides of the equation by mu equals e to the integral of p of what the f, right? What the hell is that? This is what's called our integrating factor, and it transforms your differential equation in a very special way. So let's see how this can happen. Remember, p of x is whatever is sitting as the coefficient of y here in this middle term. So what is the coefficient of y? Well, 1/2, right? So mu equals e, wow, let's try that again, e to the integral of 1/2 dx. Namely, what's the integral of 1/2? We know that's 1/2 x. We're not going to, for the purposes of this problem, we're not going to say plus c. We're just going to say 1/2 x. So mu is equal to e to the 1/2 x. Good? Step 3, actually it says multiply through by that. Oh yeah, that's continuing part of step 2. We're going to multiply through this by this guy. So we're going to have e to the 1/2 x dy dx plus 1/2 e to the 1/2 x y equals 5/4 x e to the 1/2 x. All right. Now it looks like a giant mess. You might be thinking, how did this become any simpler? This is because in step 3, this is where the magic happens. Step 3 says, once you've integrated both sides by mu, the left-hand side becomes mu times y all prime. Okay, how do I ignore? Can't hit the lock button. My lock button is broken, so fuck it. All right. This left-hand side becomes, like I said, mu times y. What is mu? E to the 1/2 x times y, and this has all got a prime on it. What this is saying is that this left-hand side is the result of what's going on here? We're multiplying these two, and we're taking a derivative. In order to do so, what do you use?
Product rule.
Right, we're saying that this left-hand side is the result of a product rule. Let's actually verify that. Which one do you want to hold constant? Pick which one you want to hold. This guy constant?
Yeah.
Okay, hold this constant. What's the derivative of y? What do we call it?
Just y prime.
Y prime or dy dx? And we leave the e to the 1/2 x alone, right? But now because you've held the e to the 1/2 x alone, we're going to hold the y alone this time and take the derivative of e to the 1/2 x, which is what? Which is 1/2 e to the 1/2 x, which is right there. Oh, isn't that really cool that happened? This is not the result of a product rule. Sadly, try as you might, you can't say, oh, this is the product rule between y and y times 1/2. No, it doesn't work. But this is really cool because this left-hand side, now that we multiply it through by this magical integrating factor, this left-hand side is the result of a product rule, namely between whatever your integrating factor is and y. The right-hand side, nothing's actually happened to this right-hand side just yet. All we've done in this step, this is where a lot of people make mistakes here, is all we've done here going from one line to the next is simplify. This was a mere simplification step. Okay? Now we want to get our hands on y. How might you suggest we do that? It's currently trapped on the inside of the derivative, so in order to cancel that derivative, we might do what?
And take the integral.
And take the integral, exactly. So we're going to integrate both sides. I got some sad news for you. Integrating these sides is going to require integration by parts, but I think it's a good thing to cover in case your professor's trying to take you around like that. Okay? We're going to come up to the top. We'll do one more line. We're going to integrate both sides. Oh, right. We're not having different color markers here. I would love to use a different color. Maybe I'll bring my own next time. Integrating both sides gives us e to the 1/2 x times y. When you integrate something, integrate a derivative, it just cancels. They're inverse functions. And integrating 5/4 x e to the 1/2 x. Let's do some quick integration by parts over here. So we have integral 5/4 x e to the 1/2 x dx. This is where we say, make a choice for u, make a choice for dv. Or we can do tabular. You guys like tabular method? That's really fast, right? So we're going to put our 5/4 x here and our e to the 1/2 x here. We're We're going to differentiate down this column, and we're going to integrate down this column. So the derivative of 5/4 x is 5/4. Derivative one more time is 0. Integrating e to the 1/2 x, this is going to be very careful here. We know that the derivative of e to the 1/2 x is 1/2 e to the 1/2 x. So the integral means instead of multiplying by a factor of 1/2, we divide by a factor of 1/2, which is the same as doing what?
Multiply by 2.
Multiply by 2. And do it one more time for good measure. Okay? And then remember, we draw lines diagonally down, upper left to bottom right, like that. Put a plus sign atop this first one, and alternate signs down each line. Multiply the corresponding terms and add them all up. So the right-hand side ends up being 5/4 x times 2 e to the 1/2 x, which means we really have 5/2 x e to the 1/2 x. And then 5 minus 5/4 times 4 times e to the 1/2 x. So minus 5 e to the 1/2 x plus c. Do not forget plus c here. Plus c is very important. And then solve for y. What would you do to both sides to solve for y?
Divide by e to the 1/2.
Perfect. Divide by both sides by e to the 1/2 x. So here's all that's going to change. If we divide both sides by e to the 1/2 x, these will cancel. And this c will pick up a e to the negative 1/2 x. I want you to pay very close attention. It picks up the negative because we're dividing through by e to the 1/2 x. So it's really sitting in the denominator and hence the negative exponent. Cool? We're almost out of the woods. I know you've boxed up your answer, but we do have an initial condition here. Namely that y of 0 equals 2. So that when we plug in 0, we're supposed to figure out the value of c that causes y to be 2 when x is 0. So let's plug in 0 for us. Actually, just plug in 2 for y and 0 for x. Well, plugging in 0 for x gives me 0 here, minus 5. Like barely visible, just barely. This chair's right in the way. 2 equals 0 minus 5, and then when we plug in 0 for x right there, I get e to the 0, which is 1, plus c. And if you had solved for c, what would you get?
7.
7. Good. So your final answer is this exact thing, but then replacing c by the number 7. That's your answer. Okay, God, I hope this works. Was there an initial condition? No. Okay, solve. And if you're not given an initial condition, you're obviously going to leave it as a general form. You're not going to be able to find c unless they give you that initial condition. All right. Step 1. What's step 1?
Divide by x cubed.
Divide by x cubed. That's going to give me... I hope this works. Okay. Then we multiply through by mu. Mu is equal to e to the integral of p of x. P of x is this 5 over x right here. What is the integral of 5 over x?
5 ln of x.
5 ln of x. How does it simplify?
X to the 5th.
Yeah, you can do it in 2 steps. One way would be to take this 5 and move it up as an exponent on the x. So you can say this becomes x to the 5th. And then we know that e to the ln cancels, which just gives us x to the 5th. So we're going to multiply both sides of that form. And this is another common mistake. Multiply both sides of this form by your integrating factor, not the original. So a lot of people would have started here and multiplied through by mu. Don't do that. Multiply through by mu here. Not in the original problem, but in the problem you've got. The differential equation you've obtained after dividing through by that first coefficient. All right. Multiplying through by x to the 5th gives me x to the 5th dy dx plus 5x to the 4th y equals x squared square root of x cubed plus 1. Do you guys see that here's x to the 5th? What's its derivative?
I have x to the 4th.
Yeah, you see that's part of that product rule that we were talking about earlier. Now, the nice thing about this is that you don't have to check the product rule, make sure that it works. All you need to know is that so long as you've done this process properly, the left-hand side will always, always, always be the result of the product rule between what two things? Mu and y. What was our mu? X to the 5th times y. Remember, nothing's changed from here, this line to the next. It's just a matter of condensing this left-hand side into a derivative. The right-hand side is still x squared square root of x cubed plus 1. And again, because we're trying to obtain y, what we're going to do is integrate both sides. So this is kind of step 3 at this point. We're going to integrate both sides. Maybe this is step 4. I don't even know what my own steps are. Integrate both sides. When you integrate x to the 5th times y prime, it just becomes x to the 5th times y. And I have yet again provided you with an integrand over here on the right-hand side, which is, it's a little bit of work to do. What technique of integration might you use to integrate this guy?
U sub.
Yeah, U sub. You might say u is equal to x cubed plus 1, and du is equal to 3x squared dx. This would transform your integral into 1/3 square root of u du if you were to approach that. Good. Integral of 1/3 square root of u, I might even rewrite this as 1/3 u to the 1/2, so I can more easily apply that reverse power rule. Adding 1 to the power and dividing by the new power gives me u to the 3/2. To divide by 3/2 is multiplied by 2/3. 2/3 times the 1/3 that's already here gives me 2/9. Shit, I don't know why I have the integral sign here. I'm done integrating. And then we make sure we back substitute. So we get 2/9 x cubed plus 1 to the 3/2 plus c. So this guy's going to come over here. Any questions so far? Is there anything that's boggling your mind? Is it all pretty good so far? And then we're going to divide through by x to the 5th. So here's what I'm going to do. You can say c over x to the 5th, or you can just say c times x to the negative 5th. That would work just as well. How was it? Was it good? For this type of problem, you might not see an initial condition given to you as y of 0 equals something. There's a good reason why. What happens if you plug in 0 to the negative 5?
Is he undefined?
Undefined. It's essentially 1 over 0 to the 5th power. 1 over 0 is undefined. So you probably won't see an initial condition like that. It might be like y of 1 or something like that. All right, let's do one more. And I think we move on to exact differential equations, or I've done a whole bunch of these, I'm not sure. Unfortunately, I didn't put any problems where there's a minus sign here, but that's also something to take into consideration there, is that whenever you're doing this type of problem, make sure that when you do e to the integral of p of x, make sure to take into account a negative if it's there, right? I didn't do that for any of the 3 problems we've done, but that's, again, something to pay attention to in case it comes up. It might though. I might be losing my mind. Okay, and we were also told y of 0 equals something. Y of 0, pi. Cool. Okay, step 1 is, remember, cosecant is really 1 over sine, so it might be best for us to multiply. You can say divide by cosecant, but to divide by cosecant is to multiply through by sine. So this gives us dy dx plus sine secant. What's another name for sine secant?
Tangent?
Tangent, well done. Tangent, yes. Sine secant is just tangent because tangent is 1 over cosine, and sine times 1 over cosine, or sine over cosine is tangent. Good? This gives us 3 sine x cosine squared x. God, I hope this works. All right, and then we're going to now find our integrating factor, mu. Mu is equal to e to the integral of p of x. P of x in our case is tangent of x. Uh-oh, this is where you have to reach into the deep, dark recesses of Calc 2 to remember this integral. What's the integral of tangent?
ln of something.
Yeah, ln of secant. On the right track. E to the ln of secant. That's nice because e to the ln of secant will just cancel and give us secant. All right, multiply both sides by secant. We have secant of x dy dx plus secant x tangent x times y equals 3. I just gotta write that down. It's a lot to write. If I multiply both sides by secant, what does this 3 sine cosine squared become?
Cosine.
Just one cosine goes away, right? 3 sine cosine. Multiplying through by secant is really multiplying by 1 over cosine. That's canceling one of these cosines. All right. Remember, once you've multiplied through by your integrating factor, you don't need to check that this is a product rule. Just trust that you've done everything right. Although a lot of people are paranoid and say, this is actually a product rule? Yeah. There's secant. That was held constant here. And its derivative, which was not held constant over here, would be secant tangent. But again, we all know, if we've trusted ourselves in doing enough of these, we say that the left-hand side always results in a product rule between mu, which is secant of x, and y. Again, the right-hand side has not changed. It is 3 sine x cosine x. This is all a matter of rewriting that left-hand side and condensing it into secant x times y prime. We're now going to integrate both sides. Integrating secant of x times y prime just gives me secant of x times y equals the integral of 3 sine cosine is, you can do a u sub there, that would be 3 sine squared x over 2. You can say u is equal to sine and du is equal to cosine. And then there still becomes the integral of 3u du. Okay. Oh, don't forget plus c. We're then going to divide both sides by secant, which is to really multiply both sides by cosine. So we end up with y equals 3 cosine x sine squared x over 2 plus c cosine of x. What's the value of c?
Let's see.
Thanks. So when I plug in pi for this term, I get cosine of pi, which is -1, but then I also have a sine of pi, which is 0. So this term just immediately gets wiped out. I'm really just left with 3 equals 0 plus c times cosine of pi. What's cosine of pi again? -1, so I get minus c. So that means c is equal to -3. So my final answer is y equals 3/2 sine squared x cosine x minus 3 cosine x. Alright, I think we've done enough of those. Now we're going to move on to mixing problems. They always do one of these questions in differential equations, and I want to show you how to tackle it. It always made my brain hurt when I started doing these types of problems, but if you just start with a few assumptions, a few reasonable assumptions, then it becomes easy. Okay, so what we're usually dealing with is like a room like this filled with saline solution, right? We're drowning in salt water. And what we imagine is there's a pipe somewhere in the back corner of the room, and it's pumping in saline solution, and there's a pipe in the other corner of the room that's draining it. So the weird thing is, we assume that when the salt solution comes in from that pipe up there, it becomes uniformly mixed with all the other solution already in there, but that's not realistic, right? Typically, we think that if this was pure water, the salt concentration would be kind of more towards that pipe coming in and less toward that pipe going out, but for the purpose of this problem, we just assume it becomes uniformly distributed as it flows in. So here's how it works. We're going to say A, I always do this, A is the amount, I guess for this problem I did sugar, didn't I? What is something sweeter? Amount of sugar in tank in kilograms. One of the best ways to approach this problem is this way. So dA dt represents what? What does dA dt represent?
The rate of change
Good.
of sugar?
Of sugar, yeah, the rate of change of sugar in the tank. Good. That would best be given by amount in minus amount out. So how much is flowing in? Well, we're going to start with the volumetric flow rate. Now, volumetric flow rate means how much volume is flowing in. How much volume is flowing in per minute? 10 liters per minute. Now this does not currently agree with our left-hand side. What would dA dt be? If A is the amount of sugar in the tank in kilograms, this is kind of on something with underlining, then it doesn't match dA dt over here. What is dA dt going to be? This is going to be rate of change of blank per blank. Rate of change of
Kilogram
per
liter. Minute.
T represents time, right?
Yeah.
So this is going to be kilograms per minute. And currently our right-hand side is in liters per minute. So we're saying, okay, shit, something's gone horribly wrong. Well, the way we can fix this is we know that the pipe carries with it a solution of sugar that is how many kilograms per liter? 0.2?
Yeah.
The pipe flowing is something to the effect that the pipe flowing in carries a solution of it of 0.2 kilograms per liter, per 1 liter. Does this now agree with that left-hand side? Yeah, the liters would cancel and give me kilograms per minute, so we're happy there. Minus the amount out, this is where things get a little tricky. In the same way, it says that the solution leaking out is leaking out at the same rate as flowing in, so it's also leaking out at 10 liters per minute. What is the concentration of the sugar that's leaking out of the tank, leaking out of the tank at that point? This is hard. This is difficult. All right, let's try. It's not in the problem. You'll be like, where the fuck is it? It's not in there. Realize that it's ever changing. That if I start with pure water, what's the concentration of sugar in the water? If I start with pure water,
Nothing.
nothing, 0, right? 0 concentration. But over time, the concentration will slowly but surely go up, right? So it seems to depend on what stage I'm at in the whole mixing problem. But the way we're going to do that is the way we're going to deal with this is we're going to talk about, we're going to define concentration as you would in a chemistry class. How do you talk about concentration? Concentration is, I guess you say moles of solution. We're not going to say moles, we're going to say kilograms of how much we have or whatever's in the tank divided by what? If I want to say the concentration of air in this room, and I want to do it in kilograms per liter, I might measure the weight of all the air in the room, right? And then I would divide by what? Well, what liters? How many liters? Would I divide by 7 liters? 15 liters? How many liters would I divide by if I want to figure out the size? I'm almost fucking give away the answer. How many liters would I divide by if I want to figure out the concentration of air in this room? That's kind of
how many liters are in the room?
How many liters are in the room? This is the volume of the room. What's the volume of the tank we're looking at here?
500 liters.
500 liters. How many kilograms of sugar are in the tank at any given time? Close. You're on the right idea, but we don't know what it is. It depends from time to time, but we don't use the variable x for that. What variable do we use for the amount of sugar in the tank? A. So put like a cloud around this or something to indicate that this is the hardest part for people to understand. It certainly was the hardest part for me to understand where they got this from was hard. This makes sense if they tell you the flow of the pipes going in at 10 liters per minute. They tell you how many kilograms of sugar are flowing along per liter. They tell you it's leaving this much. How the hell did I get this? Well, we're doing that based off of the size of the tank, we know is 500, and how many kilograms are in there at any given time. Well, we don't know that. It changes from time to time, but we do know we gave that a certain name. We namely called it A. Cool? All right. So let's simplify this. We're going to say dAdt. We're going to get rid of the units now. We're just going to say dAdt equals 10 times 0.2 is 2. 10 times A over 500 is minus A over 50. We can do this problem two ways. Yeah, we're going to have room. We're going to solve this the first way we just learned. We're going to add A over 50 to both sides. Oh, one more thing before we do that. We're given an initial condition. How many kilograms are in the tank initially? Kilograms of sugar, I should say. I think I said the solution really starts out with 20, 50 kilograms.
50.
And I said salt there. Whoops.
Salt.
I meant to say sugar. Whoops. I just changed every word from salt to sugar except that one. All right. So we're given an initial condition that's going to allow us to find the value of C. All right. What we're now going to do is. Okay, we're good. We're going to add this A over 50 to both sides to give me dAdt equals, plus A over 50 equals 2. It is in that first order linear differential equation form. Derivative with a coefficient of 1, so you say 1 times dAdt if you like, plus A over 50 equals 2. So we're going to do e to the integral of both sides. We're going to do our mu equals e to the integral of, not both sides, but the coefficient of the A term, which is what? Just 1 over 50, right? Mm-hmm. Careful, we're integrating with respect to t this time. E to the integral of 1 over 50 dt, which means our integrating factor is e to the 1 over 50 t. We're going to multiply both sides by e to the 1 over 50 times t. dAdt plus, I know it's a lot of writing. But there are actually some pretty cool implications that come out of this when we're all done. All right, we've multiplied through by our integrating factor. That means the left-hand side should result in the product between mu and A, or mu, our dependent variable, in this case A, not Y. E to the 1 over 50 t times A, all primed, equals, and again, nothing's changed on the right-hand side. All I've done on the left-hand side is simplify. Okay, integrating both sides gives us, I'm going to bring it up here, e to the 1 over 50t times A equals, to integrate e to the 1 over 50t means we're going to divide by that factor of 1 over 50, means we're going to multiply by 50, so we end up with 100 e to the 1 over 50t plus c. Almost out of the woods. dividing through by e to the 1 over 50t gives me a equals 100 plus c e to the negative 1 over 50t. This loses the e to the 1 over 50t, and this picks up a factor of e to the negative 1 over 50t. We're going to use that initial condition, namely that a of 0 equals 50, to find out that c is negative 50. When you plug in 0 for t, this tells you that when you plug in 0 for t and 50 for a, or when you plug in 0 for t, you're supposed to get 50 for a. When you do so, you solve for the value of c, giving you this as your final answer. Some interesting things I want to point out about this. When I plug in 0, sure enough, when I plug in 0, I get 100 minus 50 is 50, right? This is an exponential, but it's not a growing exponential. What term do we use for this type of an exponential? It's not growing because what happens to the limit as t goes to infinity? As this power gets larger and larger, or this